So let's look first at DSSS. But before going to DSSS, let's talk about transmission on the blackboard. So suppose that this is power and this is frequency. The target frequency at which you're going to send is somewhere. The basic rule is that the more you have to send, the more frequency you'll need to use. In other words, if you just need to send something small like voice, well, you need just a tiny bit of frequency. But if you want to send something more, like TV, then you need a lot more frequency, because on top of voice, you'll also be sending some images, and it will be in color, and there will be plenty of those per second. The amount of spectrum you use depends very much on the amount of signal that you want to send, and that amount of signal depends on how much data you want to send in that signal. Now, let's go back. Suppose that you have one signal here that is unwanted. If you send your signal, your CB or walkie-talkie signal right on the peak of that nuisance interference, well, you won't be able to hear what the other person says. So what do? Well, one technique is to use what we call frequency hopping spread spectrum, FHSS, which does exactly just what you saw. That is, say you're going to jump from one frequency to the other. Not manually, of course. There will be a program somewhere in your receiver and your sender that is going to decide on how you jump. So typically you have a certain frequency range that you have the right to use, for example the 2.4 gigahertz band. And then, okay, you see you have this interference somewhere in the middle. You decide between sender and receiver of a sequence. You'll say, all right, let's use sequence 17. And 17 means that you're going to start this frequency for a certain amount of time, and then you're going to jump to that frequency for a certain amount of time, and then you're going to jump here, and then there, and then there, and you get the picture. So sequence 17 does not necessarily understand that there is this source of interference in between. What it does is that it decides of a certain number of jumps from one frequency to the other in a certain sequence. This is why it's called frequency hopping spread spectrum, FHSS. Is it good? Yeah, it's very good, because even if you have some of your signal that is affected by the interference, well, it's not going to be affected for long, because you're hopping every now and then. And every now and then is measured in a few tens or a few hundreds of milliseconds typically. So it's not going to stay very long on that frequency that is affected. So FHSS have been used for decades, and it's a very successful technology. However, its downside is that if you have too many devices in the same area, at some point they are going to collide. So there is a scale limitation in FHSS. So there is another technique, which is to say, why instead of sending these tiny signals here and there and left and right, don't we send a large signal all over the entire band, or a good chunk of it? So that makes that if you send a signal and you have an interference, that interference is going to affect you, but instead of affecting your narrowband signal like you were affected with my walkie-talkie example, now you're just affecting a part of the communication you're sending. So in my sequence of zeros and ones here, you see a 0 and 1 which is darker gray than the other. This is the sequence that you'll be missing, because at that one frequency there is something that's preventing the signal from being heard very clearly. The SNR is too low, for example. So that technique, where you use the entire band or a good chunk of it, is called a direct sequence spread spectrum. So instead of hopping around, you just send everything in a wide wave that you send continuously. You see, it has pretty much the same consequence as FHSS. With FHSS, when you were using for a few tens of 100 milliseconds a frequency that was affected by this interference, you'd be losing that small amount of communication in time. With DSSS, you'll be losing that small chunk of bandwidth spectrum where you'll be reading the rest okay. So, in both cases, you'll lose a little bit, but you read the rest. So why use one or the other? Well, DSSS has an advantage, that is that if you have more than one device that needs to send, you can always find a way to decide which one would use which parts of the spectrum. And this typically gives a better scalability than FHSS, where again, if you have more than 10 devices, I would say, in any given area, you start having so many collisions that it's difficult to scale much more. With DSSS, scaling is less of a problem. And this is why in Wi-Fi we use DSSS. So how does that work? Let's take a laptop, and let's suppose that your laptop wants to send a 1. That's the application layer, right? You have to send that information down to the stack to the network layer. What you're going to do is that you are aware that there may be some interferences somewhere out there that will be corrupting this one if you were to send it just like it is. So what you're going to do is that you're going to convert this one into something longer. And there is a code that does that. The code is the technique by which you decide that 1 is in fact 010010001111, like you see here. There are a few ways to do that. And the one that Wi-Fi uses is called the Barker 11 coding. Barker because it's the name of the mathematician who invented that coding, and Barker 11 because 1 bit is going to be converted into 11 bits. It doesn't have to be 11, right? Some other technologies use 3 bits, and there is a Barker 5 as well, and Barker 7 and Barker 13. But for Wi-Fi, they decided that using Barker 11 was a good combination. Why is that? Well, because 11 gives you enough resistance to noise and interferences that you can survive the loss of up to 9 of these 11 bits and still understand that you were sending a 1. So it's very robust. So you take that sequence, that long values now of 11 bits, and you're going to send those numbers in parallel over this spread spectrum signal like this. That's why you were seeing the wave in the previous slide showing that none of these numbers being sent in parallel. To get into the nitty-gritty details, each bit takes 2 megahertz of frequency to be sent. So if you need to send 11 in parallel, you need to have 22 megahertz wide frequency for your transmission. So that's the size of the DSSS basic transmission in Wi-Fi. Okay, so that's nice. And by the way, as we are at the naming convention, things that you may want to remember. The one that you want to send initially, that's the data that you want to send. Okay, that's easy. When you convert that data into that long series of 11 bits, what you get is a series of chips. So when you talk about data, it's the real data you want to send. When we talk about a chip, it's still the 0 or a 1, but instead of being the 0 or the 1 you want to send, it's the representation, part of the representation of what you want to send. So we have 11 chips in the Barker 11 coding. And all that thing together, the entire sequence of 11 is called a symbol. So we are sending a symbol of 11 chips, and altogether they represent the 1, the data you want to send.